Assalamualaikum dear student. Today we have week number 14 and lecture number 1. In this lecture we will study Turing machine. Why we need Turing machine, we will see the importance of Turing machine in the upcoming slide. We had studied three mathematical models. That were finite automata, transition graph or transition table, push-down automata that were studied. These three models have used whether a string of input language is accepted or not, right? Such models are called language identifiers. However, we have also some languages which cannot be accepted by the above three mathematical models, right? For example, there does not exist any finite automata or transition graph or push down automata accepting any non-context free languages. So for this purpose, the topic is coming, or another model is coming. This is called Turing machine. Okay, this Turing machine has been invented or developed by Alan Matheson Turing, right? That machine called Turing machine, which accepts some non-context-free languages as well as also accepting context-free languages as well. Okay, so that is the person who proposed Turing machine, which accept both type of strings. Okay, non-RFC and CLS as well. Before going to the detail of Turing machine, we have some basic definition. In this basic definition, we will study the components of Turing machine, how a Turing machine can be designed, and what are the components which based on design of Turing machine. So the first one we have an alphabet of input level. Second one we have that is the input tab. Okay, tab, that is actually the keyword which is used for Turing machine. You can use any word to Turing machine. Okay, but for general understanding we are using a tab. Okay, that is actually the input alphabet, like it could be A, B, 0, 1 or anything. So we generally we represent that is the input tab. Okay, the input tab are partitioned into different cells. Okay, this cell have the same definition as we know from the memory concept. Okay, that is the ROM and the RAM concept. So both have one location, whether it will store 0 or 1, or another word we can say 1 or 0, or another word we can say A or B. So in this complete partition input tab, we have a finite number of locations in one direction. Mean to say, it could be read from left to right side. Okay, the input string is placed on the tab string at first letter on the cell I. Okay, what is cell I? That is actually the location of the cell. Okay, right? Or it could you say it's denoted by cell I, J, K, and so on. You can say, even though you can also use 1, 2, 3 or A, B, C. It's up to you. But usually in mathematics or such subject we use I, J, K, X, Y, Z, and A, B, C. Okay. So in this case, whenever we have the first letter from the input string, so we will place in the tab string, this tab, that is the location cell I. Okay, the first word. The rest of the tab is initially filled with the blanks letter. Okay, so here we represent the blanks by this delta symbol. Okay, that is the end, or that is we also call halt or stop of the Turing machine. Okay, to stop the processing further. That is the example of the input tab partitioning into different cells. Okay, this you see Roman 1, 2, 3, 4 up to infinite number. Okay, and this is the cell location actually 1, 2, 3. And this we have inserted that particular input value. Okay, this is like over here we have A, B, A, and this is the stop symbol, okay, or termination, okay, to stop the processing. At the first location, that is we call the tab head, okay, that is represented by this symbol, okay, this is the tab head. This is the arrow symbol, which shows us it's the starting of the Turing machine input values. If we see this input tab, that is like a pointer concept. Okay, so whenever we need to move, so we just call the address of the next cell. So this way, it reads the next content from the input tab from left to right, and whenever it reads the empty symbol, so it stops the processing. Okay, so the point 3 is the same purpose we have over here. So step 3, a tab head can read the contents of a cell on the tab in one. It can replace the character at each cell and can reposition itself to the next cell, to the right or to the left of that. It just read the text. Okay, it can go to our right or it can go to our right left. It depends on the input directions. Okay, so we will see that one as well. And whenever it want to move from one cell to another cell, so that is called reposition. Okay, reposition or moving to the next cell. So this is the concept about this thing. We have another point here as well. Like we are in the first or initial position, starting position, so it cannot further move toward the left. Okay, if we move toward the left, so it means we are doing violation. Like for example, in RAM or in ROM, if we tag the position of operating system file, so we will just crash the machine. Okay, so same case is over here. If we try to move toward left, which is not possible, so it means we are crashing the system. Okay, so this is one of the example. So here we have same explanation. Initially, the tab head is at the cell I. Okay, in the starting point. The tab head cannot move to the left of the cell I. The location of the tab head is denoted by the start symbol. Okay, so if we do violation, so it means we are crashing the system. Next, point 4, we are discussing the output from the Turing machine. An alphabet of output of the character that can be printed on the tab by the tab head. Output may include the letter of input, of course. Even the tab head can print the blank or the stop symbol as well, which means to read some character from the tab as well. Okay, so this is the way whenever it moves from left to right, right. So actually, it's printing, it's reading the data and printing the data on the tab, output tab. Okay. Similarly, in Turing machine, we have finite set of states. One is the starting symbol, and the next we have the final state. Okay, so here we replace the final state with the halt, mean the stop state, which means to stop the execution of the system and reach to the final. Okay, so that is the halt state over here. Okay, so here we have representation for the input state, right? The next state, and it is going toward right or left. So that is called a program. Okay, so in that program we have a set of rules. So what are actually the that set of rules? Like if we move from current state to the next state, okay, so it will, like for example, show Q1, and then we have the output of this Q1. Mean the Q1 is the state, and next, like for example, A, so that is the output of this Q1, which is replaced by Q1. And next, for example, we have R or L, mean left, right or left side. Okay, so this is the program actually we use the Turing machine. So let's read from point number 6, a program which is the set of rules which show that which state is to be entered when the letter is read from the tab. Okay, so that is mean we are starting from the initial state and we are going to read the further state, and what could be the input from that particular state, and what could be printed from that particular state, right? And what character to be printed, right? This program is shown by the state connected by the directed. It is labeled by the triplet. Okay, triplet means we have three information in that particular one case. So here they mention letter direction. Okay, so this letter means that is uh, the state number. Okay, if we moving from state 0 to state 1, so that is actually show will q1 state 1. Okay, and this second letter, that is the representation of the output value of that particular state. Okay, so that is mean the q1 will replace by particular state output like a in the input tab or the output tab, and the direction mean whether it's going toward left or right. So that is important thing. Okay, so we will see in the coming diagram how we can implement letter and direction. Okay, so this is called combinedly triplet. It may be noted that the first letter is a character the tab head read from the cell to which it is pointing. Okay, whenever we start from the initial cell, so it means it pointing the starting of the head, which is reading the particular letter. Okay, the second letter is the what the tab head print the cell before it leave. Okay, whenever it move to the second letter, so it will print the first letter, mean the previous letter. The direction till the tab head, whether to move or to go one cell to the right or one cell to the left, right. Okay, so that is the important thing. So already explained our here letter and direction. Okay, so this is the explanation of the previous letter direction, which is the called triplet. So there are some observation about the whole elements used in the Turing machine. It may be noted that there may not be any outgoing edges at certain state for certain letter to be read from the tab. Okay, this is a very important point, which creates a non-determinism in Turing machine. It may also be noted that at certain state there cannot be more than one outgoing edges for certain letter to be read from the tab. The machine crashes if there is no path for a letter to be read from the tab and the corresponding string is supposed to be rejected. Okay, so this is about the whole summary which was reflecting to the Turing machine. And I said before all of the point which is mentioned here in this note. So hopefully you have understand how it works. Okay, so let's continue. To terminate execution of certain output string successfully, we use a halt state must be entered and the corresponding string is supposed to be accepted by this Turing machine. Like we here successfully read this first letter A, and we want to like terminate or we want to move to the next. So the letter head or the tab head will move to the next cell. Okay, toward the right, print with this and this, and finally it will stop. Mean we have finished all of the input character. A halt set must be entered and the corresponding string is supposed to be accepted by that Turing machine. Okay. The machine can also crash when the tab head is instructed to move one cell to the left of I. This I explained very earlier. Okay. So it is mean we are doing violation of the operating system or design of the Turing machine. Okay, so we have in the rule of Turing machine, if we move towards right, if we are at the beginning of the state, so it means we are crashing the system. So that is an important thing. Okay, so we have some basic example on Turing machine. If we see from this Turing machine, we have the start and we have the final. So here the final has been represented by a halt. Okay, so it is very important over here. We have to say start 1, which represent the starting or start state, and the final state, which represent halt, and this is the state number 4. Okay, so let's explain this figure. We start from here. Okay, start. Okay, so if we see over here, we have AAR. What does it mean? A is the state, and this A replaced by this state, which is mean this one to here, okay, and or we are moving towards the right side. Same for the below case BBR. This B represent the state and this P represent is the value, okay, which will replace by this state B, okay, and we are moving towards right. Same case over here. So we have BBR, okay. 3 have a loop, okay, a loop. So we can represent the loop in this way, okay, like state value and R, state value and R, okay. So we can read either A or B, okay. Before going to the final state, we have to stop the system, otherwise it will crash or it will down, okay. For this, we use empty empty and or mean to say stop over here. This is the final. So it means and from this machine we can say it is accept A B A. So that is the input A B A, okay, and it also showing us that this Turing machine accept A B A as well, okay. It will depend whether we want B B in A or we say A B and B, okay. That will depend on the input query from the user. So this is about how a Turing machine can be designed. Okay, so already we have done with in the instruction of Turing machine, okay, start symbol and the stop symbol, and then we have triplet, okay, and how we can stop that machine, otherwise it will crash down, it will fail the complete architecture. So here we have again that is the input is ABA from which is accepted by this Turing machine. So how we can represent in the transition Turing table, okay, which is the input tab actually, okay. So this is ABA and this is the cell number 1 2 3 in the Roman form, and then we have stop, okay, to protect the system from crashing down or from violation as well, okay. Starting from the start state, actually this one is reading, okay, reading A from the tab, and according to the Turing machine program, A will be printed as usual, okay. Like for example, A will be replaced by A, this one actually talking, okay. This is the state, this is the value, and this is toward going to the right side. Replaced by A, and the tab head will be moved one cell to the right, okay. So it will finish the reading, so definitely it will move to the next cell to read the next letter. Okay, so which can be seen after reading the letter A, so the tab had moved to the cell 2, okay. And so in this way we have complete the reading for Turing machine, and then we stop and file. Like here we have the example. This process can be shown. Like we have at one, at step 1, like you can say start. This is A, okay. So still we have to read BA, okay. So at 2, step 2, so we will read B, and similarly we will read A as well, okay. So we perform all of the action in 3 steps. Okay, at step 3, reading A will keep the state of the Turing machine unchanged because that is the last word of the input value. Lastly, the empty or the blank symbol is read, and this blank is replaced by blank, the empty state, which stop or which halt the state. Okay, read, we can say it read the state of the halt, which can be expressed like this way. So we have start, second node, third state, and third state, which is we are going before reaching to the hard state. So we have to read the empty or empty string, okay. It will know from the diagram, okay. So finally it will stop over here, which shows that the string AB is accepted by this machine. It can be absorbed from the program of Turing machine. The Turing machine accepts the language which is expressed below from the given pattern. So we can say B is the common here, okay, and A plus B and A plus B whole square. So that is an important thing. Okay, so that's why we are preferring the Turing machine instead of the other mathematical machines. We have some theorems. The theorem again, like even number, odd number, palindrome. Okay, so that is again the theorem for Turing machine. How we can see even language, odd number, or palindrome as well. Okay, so consider the even language following the Turing machine, accepting the even language. How? Let's see. Okay, this is the start. Okay, in the start we have also on the left side we have a stop as well, means stop of the machine. Okay, so like for example, why it has placed the halt over here. If we know from the definition of even, so 0, 2, 4, 6, 8, so these are coming in the even language. Okay, that's why it has been put it very close to the start. This means the stop or the halt. So this is the, if we see, um, start, so BB, right, and then again BB, right. Okay, so it depends. We have to achieve the even, okay, like AB, AB, BA, right. So already we know how we can design. We already know from the finite automata. But this tuning machine actually protect the even number of A, the even number of B's. Okay, so they have given the direction as well, and finally it will stop as well. Like for example, if it is even, okay, so like this is the BB, okay, B, okay, then we have to read the A, okay, then we have A, then we have B, and then we finally stop. So this is the way how we can achieve. Okay, so already we know about in the previous lecture how we can achieve even. So this is the same thing, only we have added extra feature or for Turing machine. Consider the another example for Turing machine, the same. Okay, so we have the start and halt. Okay, so like here. Okay, it is also possible we can replace a state with a static as well. Okay, that is depend. Okay, like here, the state the static and replace with the video static. Okay, empty as well, empty as well. Okay, so same as cases here. Okay, it just show we can have mini type of Turing machine. This is the example. Okay, the string triple A, triple V, triple A can be observed to be accepted by the above machine. Okay, so it is actually printing 3 times A, 3 times B, and 3 times A. So it can also be seen that the regular expression for the above Turing machine, that could be A the power n, B the power n, A the power n as well. Okay, so that is why. Which also say this is non-context-free languages. Okay, so hopefully you understand this language, this lecture as well. Okay, thank you so much, Aslam.